All right, so what we want to do is say that if we have a set C, which is bounded and has measure 0, and the integral of the indicator function exists, then show that the integral is 0. This is actually sort of interesting because when you actually define the integral in terms of measure theory, basically what you define, well, you start by defining a measure of a set, and then the first types of functions that you integrate are these indicator functions. And you define the integral of an indicator function of a set to be precisely its measure. So in this context, if this should be consistent with that more advanced definition, then a set of measure 0 should have, if a set has measure 0, that should be equivalent to the integral of the indicator function of that set also being 0. And that's what we're doing here. Although we're not proving both directions, we're just proving one. Because the other direction should also be true. If you've got an indicator function and it's 0, yeah. Anyways, let's just do this problem. So we want to prove, as the hint suggests, that the lower sum is 0 for any partition P. So let P be a partition of A, and choose any set U in this collection P of rectangles which cover the space A. All right, so U intersected with C is a subset of C, obviously. So the measure of U intersects C equals 0. This notation, again, means that U intersects C is a set of measure 0. Okay, so basically what we want to do is we want to look at what is the lower sum going to look like on this particular set U. So anyways, U intersects C is 0. So if we're given any epsilon, we can cover a set of measure 0 by rectangles whose total volume is less than epsilon. So what we're going to do is we're going to set epsilon to be the volume of U divided by 2. So let U1, U2, etc. be a collection of sets that cover U intersects C, such that the sum from I equals 1 to infinity of the volume of Ui is less than epsilon. And we know that this can be done by we know that this can be done because U intersects C has measure 0, and so this is the definition of being a set of measure 0. So anyway, so the UIs cover U intersects C, but the UIs do not cover all of U, because U is a set with volume, well, epsilon is the volume of U divided by 2. So if you were to take the union of all the UIs, that would have total volume less than the volume of U over 2. So you're only covering at most half of the points in U. And so at least half of the points are not covered. So the UIs do not cover all of U because there's not enough volume, i.e. there exists some element X which is in U and not in the union from I equals 1 to infinity of the UIs. And this, of course, is a subset of U set minus C, because the union of the UIs contains C. So if you take U and you remove all of the UIs, then you're certainly removing C. Okay, so there's an element X which is in U but not in C. So the mu of chi C, which is the infimum over wait, hold on. Let me think about this. Oh, right. This is the supremum, or no, this is the this is the infimum over all x and u of chi C of x. So this must be less than or equal to chi C of x, because x is in u. But this is 0. So if we take the infimum over all elements of u of chi C, then we're going to get a value which is less than or equal to 0. But chi C only takes on the value 0, 1. And so it must be the case that this infimum is precisely equal to 0. Now, this holds for every rectangle U in the partition P, so the lower sum of chi C P, by the way, this F, this is obviously chi C. They must have just not replaced it there. No big deal. So this is, remember, by definition, this is, you take the sum over all elements in the partition, you take this infimum thing times the volume of U. And for every U and P, this mu of chi C is 0. So this entire sum is 0. So for any partition P, the lower sum is 0. So that means that 0 is the supremum over all P of overall partitions P of this lower sum. And since this is an integrable function, this is equal to the integral over all of A of chi C. All right, and that's what we wanted to prove. There are two things that bother me about this. The first one is that it says use problem 3-8. 3-8 states that any rectangle does not have content 0. I don't really see how that's relevant here. But so it's possible that I'm missing something, but I think this argument should work. Yeah, you just take any U intersect C, and you cover it, and you're good to go. So yeah. The other thing is that we didn't use the fact that C is bounded. It says if C is a bounded set of measure 0 and this exists, show this. But again, I also don't think that's really super relevant. I don't really see why that should be necessary. And in fact, when you talk about measure theory, like, it's perfectly fine for sets of measure 0 to be unbounded. And you can integrate the indicator function of an unbounded set of measure 0, and the result will be 0. Take, for example, the set of rational numbers. The set of rational numbers is an unbounded set. And it is a set of measure 0. And using measure theory, you can define an integral of the indicator function of the rational numbers, and the answer is 0, which is precisely the measure of the set of rational numbers. So there could be just some simple thing that I'm forgetting about the specific definition of integrability that we're using here, where you need this set to be bounded. But I think this argument works. And assuming that it works, we're done.